Hello, everyone, and Steve Carey. This is to continue my video try to explain malus without superposition. And you'll recall that malus is the cosine squared and sine squared of theta ratio of passing and failing when a photon goes through a filter, where this is the photon angle and that's the filter angle. And remember we said the photon was like a frisbee trying to go through, and if it's polarized in the direction of the filter, it goes through, but if not, it doesn't go through. So we were trying to explain what happens if it's at an intermediate angle, and so that angle is theta, and by the law of malus, it will pass cosine squared theta of the time and fail cosine squared theta time. We're trying to explain why it's cosine and sine squared. Now, the traditional explanation is that the photon is superposed as a superposition of states, one at this angle and one at that angle. And but it's not that it's composed of two different photons, it's that the probability is composed of these two different vectors. And it's not just the probability, it's the amplitude of the probability, so you have to square it to get the probability. Well, it's just like the amplitude of a wave in the ocean has to be squared to get its intensity. So that sort of makes sense, but the problem is that causes a decrease in power if you're just using that much of the amplitude. You recall that a photon is really an electromagnetic wave oscillating back and forth with the electrical oscillation going in one direction, and there's a magnetic oscillation going in the opposite direction. So when it hits the filter, what they say is the amplitude in this direction gets passed. The amplitude in the other direction does not get passed. But that would require a decrease in intensity. And what happens is that if it's a photon, if it's a particle, when it goes through, nothing is decreased. So you have to explain how it goes through unaffected. Well, my idea is that when the wave hits the filter, it gets pushed to one direction, passing, or the other direction, failing. It gets pushed by a cloud of vectors in the filter, acting like Brownian motion. Now, this is a cloud of vectors of limited power, radius 1, but there's the vectors push in all directions. And if you were the size of an atom, this cloud of vectors would look like that, kind of a bush. Now, not all the vectors will be successful. Only the vectors, for example, down here you see, only a vector aligned in this direction will push the photon polarization vector into the pass direction. And the length of that vector is sine theta. And to make it fail, you have to have a vector in this direction. And these are picked out of this cloud. So how many of these successful vectors are there? Well, there's just one that's exactly along the line here, but I'm thinking that any vector in that cloud that has this component in it will push the plane of the electromagnetic wave into the right orientation or the wrong orientation. So there's many vectors that would be successful to make it pass or make it fail. So how do we count those? Well, that would be this subset of vectors in the Brownian cloud that consists of all the vectors that strike this disk here. And all those vectors would have this component. Well, what's the radius? This is a disk. that is a slice through the bush, making another disk. See, it's a disk. A slice through the bush makes a disk. So what is the size of that disk? Well, the radius is cosine theta for this disk. So the area of the disk is cosine theta squared pi. Now what's the radius of this disk? That is sine theta. So the area is sine squared theta. So we have this relationship between the passing and failing successful vectors of cosine squared and sine squared. They add up to 1, and that is exactly the ratio of malus. And we've explained why it's squared without superposition. So check it out. There's more to come later.